So now we're going to look at how we can use this tangent plane to approximate the function near the point of tangency. All right, so an example is in order. Let's estimate the following quantity: 2.01 squared minus 0.99 squared. Now obviously we can stick this in our calculator, but we want to use the tangent plane to the function x squared minus y squared, which you can see this is being evaluated on that function at the point 2, 1. All right, so we've already found this tangent plane. It was the equation earlier, so we have z equals 4x minus 2 minus 2y minus 1 plus 3. Let's draw the picture. So it looks like this. So our tangent plane at this point looks something like this. And it has slope 4 in the x direction and slope -2 in the y direction. And because the tangent plane is really close, really similar to the surface at points near 2, 1, it looks like a patch on the surface. It's really similar to the surface. If we evaluate for points near 2, 1, which is this point right here, then the function and the plane are going to output really similar values. So let's put in 2.01 into this plane, and we can do all the calculations by hand, and we can compare that to what we get when we just do this with our calculator. So if we do these by hand, we'll get 0.04 plus 0.02 plus 3, which is 3.06. And because the function is really close to the plane, near 2, 1, this function output's going to be close to 3.06. We don't know what it is. We can throw that in a calculator if you want to see what it is, but it has to be close to that because we're at a point really nearby 2, 1. Let's consider another example. So let's look at the distance between the origin and the point xy. And the formula for this is something we've talked about. It's the square root of x squared plus y squared. And if the distance between 3, 4 and the origin is 5, that's easy to check. Estimate the distance between the point 3.1, 4.05 in the origin. All right, so we want to use the tangent plane to approximate this function, this curve. And the way we do that is we look at the partials to find the slopes in the x and y direction. So the partial with respect to x is going to be, well, it's going to be 1/2 x squared plus y squared to the -1/2 times 2x. Simplifying, we get x over the square root of x squared plus y squared, which if you put 3, 4 into that, you get 3 over the square root of 25, which is 3/5. In a similar fashion, the derivative with respect to y is going to be the square root of x squared plus, y over x squared plus y squared with a square root over it. And if we put 3, 4 into that, we'll get 4/5. So those are the slopes in the x and y directions. And now we're ready for our plane. So our plane, which we'll call z, we could call lxy. Well, maybe I'll call lxy this time just to familiarize you with the notation, is going to be 3/5 x minus the x coordinate of the point, which is 3, plus 4/5 y minus 4, plus the z coordinate, which is 5. And now we're going to put in 3.1 comma 4.05, and this works out to 3/5. 3.1 minus 3 is 0.1, plus 4/5. 4.05 minus 4 is 0.05, plus 5. And 3/5 of 10 is 6, so this is going to be 0.06. And 1/5 of 0.05 is 0.01 times 4 is 0.04. So this adds to 0.1, so it's going to be 5.1. And so the conclusion is that the distance between the origin and this point, 3.1, 4.05, is approximately 5.1. And if you actually put this in your calculator and have the calculator do all the work, you'll get 5.100245, etc. So these are indeed close, and the plane is doing a good job of approximating the function.